Hi everybody, this is Aaron Schwartz, and this video is called Rooting Around, and it's part of the Unit 5 exploration for the Algebra video series. We're actually looking at using patterns from quadratics to frame root functions. In Unit 5, students learned about the square root, cube root, absolute value, step, and piecewise functions by exploring patterns in diagrams, tables, and graphs. Some of the key ideas include that a square root function is a type of opposite of a quadratic function. Another key idea is the rules for transformations of quadratics, k times some function f of k times x, f of x plus k, and f of x plus k are the same for all function types. Some of the skills that students have learned up to this point that will be helpful is that in mathematics, there are many different types of opposites that we call inverses. This is developed all throughout elementary school and all throughout Algebra 1. We also have learned in previous segments of the algebra curriculum that quadratic functions have a linear rate of change and a constant second finite difference. This is done a lot specifically in Unit 4, Topics 1 and 2. So let's start talking about root functions. In earlier videos in Marking Period 3, we explored quadratic functions, their linear rate of change, and the constant second finite difference. So one of the things that we might want students to look at is a simple quadratic. We've asked students to do this in the past. We've asked them to look at what is the first difference and what's the second difference. But what we're going to do differently is give them an XY table without any explanation, and we're going to ask them to find the second and first differences and see specifically what they notice. Now, we're not going to really give them any more details other than this table. Some students are going to immediately notice that the x and the y values seem to be reversed. In fact, when I've given this table to students cold without any explanation, the first reaction is, Mr. Schwartz, your x and y values are reversed of what they should be. After students notice that, or if they notice that, acknowledge that this is backwards from what they have typically seen, but it is a correct table of values, and to keep moving. Some students are going to immediately start to find the first and second differences, but what they're going to start to do is find the first and second differences of the x. They're going to notice that the x has a linear rate of change, and that the second difference of x values is constant. So this is in sharp contrast to that x squared function we've already explored. In fact, it's the reverse, or it's an inverted approach to it. This time the y's have a constant rate of change, and it's the x's that have a linear rate of change. So we might want to ask students some questions about what implications this might be. What might this function be? What might the equation be for this? Some students are immediately going to pick up that it's going to be something like x is equal to y squared. Some other students may jump on the idea of a square root. But whatever we do, as students are noticing these things, we want to steer them in the direction of the fact that you've got some inverses going on. Something is inverted from what we've previously seen. We may even want to ask them, well, what's the inverse of squaring something? And they may say the square root. And so what we're going to be doing is getting into that idea of functions as inverses. We can now start to introduce the graph for additional depth. And here we have a graph that was generated in Desmos, but the key idea is that I can contrast the quadratic now with that square root function. And I'm going to want to ask students what they notice. And they may say things like, wow, it's the x and y values that are reversed, at least for the positive values. And so now we can really add some depth to this idea of a square root as an opposite or an inverse. What we've really done is we've inverted what we would normally do with a quadratic. And we can now introduce the equation f of x equals a times the root of x minus h plus k. This is going to be a very big notice for students because they're immediately going to launch onto a, h, and k. Wait a minute, we've done that. And the moment they do that, it makes it so much easier to introduce this material, because what you're really telling students is all those rules that we have learned when we were looking at quadratics, guess what? They apply for any type of function. In this case, we're dealing with something called a square root function. And we can now show them that, in fact, a square root has a type of vertex and that the rules are still going to apply. Now, in Algebra 1, we really don't look at the vertical dilation for square root functions. We really just focus on the translations. But actually, they're the same values, and students could have an interesting exploration with an interactive graph. They could also start to look at A in terms of that reflection. How do we get the bottom half of that parabola? Because when we look at the square root function, we only see essentially a top half of that sideways parabola. And so A becomes an exploration in getting that negative side of the square root. So let's start talking some more about cube root functions. So cube root functions operate on very similar properties as square root functions in the sense that we're going to be doing an inverse. So one way of introducing this is to tell students we're going to take a look at a new type of function. It's a cube function. We've looked at quadratics, which are squared. Now we have this cube. And we might ask students, we might give them some direction, say, you know what, find some constant differences for those x cubed values. And they may notice that there is not really a clear pattern in the first difference, but if they take a look at that second difference, they may see a pattern. And then they may see a linear difference in that second pattern and a constant difference in the third level. And this gets back to some calculus ideas. When you have a power function, that power indicates at what point you will get a derivative that's constant. And that's what we're seeing here. At that third set of differences, we finally see our constant difference. And that's really interesting, but we actually want to move to cube root functions. So after students have explored this, we're going to do the same thing we did with the square root. We're going to reverse the table and ask students what they notice. Obviously, they're going to notice the values are reversed, but then we might ask them, well, what things can you predict? And they might predict that the x's are going to have those rates of change. First, there's going to be a quadratic rate of change, then a linear rate of change, and then a constant rate of change. At this point, we can start introducing the graphs. And we can show them that unlike quadratics, a cubic function, one side goes up and one side, as you're going towards the negative, is going down, or what we can talk about is end behavior. What does it end behavior mean? And then we can see that in the cube root function, we don't have that same truncated domain because that tail can go off towards the negatives and still maintain that the inverse is a function. And so students have this rich opportunity to explore it. From here, we can introduce the equation for the cube root function. And again, it's f of x equals a times the cube root of x minus h plus k. At this point, students are going to immediately say, oh, I know what the transformations of this function are, but I've never even spent more than 30 seconds exploring this function. And that is the key learning we want them to walk away with. They can know the transformations of any function just by taking a look at the equation in a particular form. So some sample questions that we might use as assessment items might be the two that we have on the screen. Number one, which functions must contain the point 1, negative 3? Well, in scanning through these, we're looking for that vertex form. We actually don't even care what type of functions it is. We're just looking for x minus the 1 and then the minus 3. And so any functions that have that format are going to contain the point 1, negative 3. So f of x equals 2 times the absolute value of x minus 1 minus 3. That's going to have it. In fact, the first two functions are definitely going to contain the point 1, negative 3. The second question, which functions have a domain of x is greater than 2? Well, if we've already done some exploration with absolute values, this one's going to be particularly easy, because really we're just looking for which of these types of functions is going to have a restricted domain. And the answer is G. All of the others have a domain of all real numbers. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.